So Maggie promised that I would give a very quick presentation on how to take some of the techniques that we used in the class, which we coined slicing and dicing of matrices, and do how to parallelize that. So last night I sat down and actually put it together, and that has some of challenges. There was a post that instigated this, where way back in week 1 or week 2, maybe it was week 3, I don't know. It's all a blur. Someone mentioned that doing the matrix vector multiplication by rows was better because it parallelized better. And I happen to have written some papers on that. So Maggie said, well, you know, as the final presentation, you should do a talk on that. And I said, oh, okay, fine. You know, that was a long, long way away. And I thought it'd be okay. Notice that when people talk about parallelizing, I tend to think of massively parallel. So here is a picture of Stampede, which has 500,000 cores. And the question is, can we do a matrix vector multiply on 500,000 cores? And that's what I'm going to look at. So the way to view this, here's a picture from, oh, I think it was week 5, that gave a very, very basic overview of what a processor looks like. And you know, think of taking one of those and duplicating it many, many, many times. And bingo, you've got yourself a massively parallel architecture. Of course, things are a little bit more complex than that, but let's just keep this picture in mind. Now, what I'm going to do is I'm going to switch to slides I put together in LaTeX because I feel so much more comfortable with that when things get technical. So there's some basic assumptions that we're going to make. Okay, we're going to look at a matrix that's n by n. But think large, okay? A matrix that would fit in the combined memories of a huge machine like that. Million by million or something like that. We're going to have P processors. And here's the really odd part. I'm going to take n to be a multiple of P plus 1. And there's a reason for this, okay? The reason is that normally when I teach how to do a parallel matrix vector multiplication, I first teach about collective communication, which is how to move data around on these machines. And then I use matrix vector multiplication as an excuse to show how the overhead of communication gets in the way of being able to scale to very large numbers of processors unless you do it right. The problem, of course, is that I would have to go and create a MOOC on how to do parallel computing in order to give people the background on how to understand this. But about 10 or 15 years ago, I noticed that I could actually do all of this without worrying about the overhead of communication, if only I assume that n is not a nice multiple of p. If it's just one more. Why? Because the load imbalance that is then created is of the same order of magnitude as the cost of the communication that needs to be done. So any conclusions about a matrix being bad simply based on load imbalance carries through to an argument saying, and if you then did communication, things even get worse. Okay, so that's the argument that I decided to make. And we're going to take the cost of performing a floating point operations to be gamma. So think of that as a micro bleep in seconds or something. Now, back in week 4, we looked at the dot product based matrix vector multiplication, and I sort of stepped through it where we ended up doing dot products of rows with the vector. And then we moved on and we said, oh, but we can instead think of slicing and dicing this, where we take our matrix and we simply partition it into P submatrices, and that's something that is part of the course on how to think about that. And you do the same thing with the vector y, and you don't partition x, and then you do a partitioned matrix vector multiply to find out that really you just need to do matrix vector multiplies with the blocks. And bingo, the parallel scheme is kind of staring you in the face. Namely, you can compute the ith subvector of y by performing a matrix vector multiply with the ith block of A and X. All right? Simple enough. So the question then is that good? Well, communication happens too. And let me illustrate that a little bit. Typically you assume that the matrix is already distributed, so there's no cost to that. Then somehow magically X appears, and then you can locally simply compute the subvector of Y. And you might look at that and say, oh, no communication had to happen at all. All you had to do was assume that all of these vectors and matrices were distributed this way and everything is good. Except that in week 12, people learned about the power method. And as part of the power method, you not only do a matrix vector multiply, but you take the result of that and feed it back into the next matrix vector multiply. And what that inherently means is that you really want to say, let's start with pieces of X distributed like the output vector. Let's then collect all of those together. That's called an all-gather in collective communication. Then you do a local matrix vector multiply to compute a subvector of the result vector, and then you can feed that back in and keep doing that. So, but we're not going to worry about that communication because we can already show when an algorithm is bad or good while saying, communication comes for free. And how does that work? Well, we do a cost analysis. A matrix vector multiply costs 2 n² floating point operations at a cost of gamma seconds, whatever, each. If we parallelize it, notice that you have to assign rows of the matrix to the processors. And the ceiling function, computer scientists are very familiar with. This is really let me get it right, the smallest integer greater than or equal to n divided by p, right? And notice that by the way we define the problem, it doesn't divide nicely. There's always going to be one row left, okay? And that's going to be important, okay? And that we describe as saying, look, n we took to be some multiple of p plus 1. And if you do that, then you know that when you divide by p, you get 2 times k plus 1 times n gamma. So then people are interested in the speed up. How much faster will we go? And that's just the time that we estimate for the sequential implementation divided by the parallel. And if you do that, you just plug in the numbers. And if you fudge around a little bit, you get this. And then there's something called efficiency, which you would like to be 1, which is the speed up divided by p. Come on in, guys. And that's just this number divided by p. And if you then mess around a little bit with it, you end up with this expression right here. Okay? And the question is that good or is that bad? Because now we have an estimate of how long it will take, what kind of efficiency we will get as a function of n and of p. N was the size of the matrix. P is the number of processors. Okay, well, let's play around with that a little bit. How many of you are optimists? Okay, Field is an optimist, so is Farhan. All right. What would the optimist say? Well, optimists would say, well, just fix the number of processors and make n really large. And if you do that, p is fixed, n gets very large, and you notice that eventually this is inconsequential relative to n, and you get an efficiency of 1, which is the best you can do. This is good. All right? How many of you are pessimists? Okay, Pierce and Josh are both pessimists. The pessimist will say you fix n, and you let p get large. You say, look, I have a fixed problem I want to solve, and I want to throw as many processors at this as possible. And if you do that, then p gets very large, but n is fixed, and you notice that eventually you start dividing by a very large number, and you get an efficiency of 0. That's bad. Okay? So all I need to do is convince you to be an optimist, and everything is okay. Right? Well, there's a third category of people. And before we get to them, let's talk about weak scalability. Weak scalability says the following. We have one of these machines. We can add more processors to it, but notice that every time you add more processors, you also add more memory. So then we can do a larger problem. So if we just scale up the problem every time we add more memory to it, can we retain efficiency? If we were running at 80% efficiency, can we run a larger problem on more processors, 80% efficient? Okay? And the easiest way to look at this is to say, look, you buy these machines to do big problems, so we will put the biggest problem on there. Can we run the biggest problem efficiently if we increase the number of processors and we increase the problem size corresponding to how much memory we add?